little bit more practice to wrap up our study of Laplace transforms, with particular focus now on the unit step function, our on-off switch, and a little practice with the delta function as well. All right, let's begin. Find the Laplace transform of the function shown in the picture below, and assume the up-down pattern continues. So we have this up, down, up, down, up, down, so it's going to go up, down forever and ever. Okay, well, what do we do? Well, looking at the picture, we see that there's behavior changing, right? Because each part of this is a line. It's just a series of lines connected together. And so when you have a change in behavior, it's a piecewise function. So we should talk about our pieces. So let's go under each interval and figure out what the pieces are doing. Well, the first part, that's pretty easy. We see it's going up, and so that is the function t. Now, the second part, well, we're going down now. Okay, so what do? Well, the slope is -1, so it's a minus t. And then it's, well, you got to figure out the y-intercept. But actually, we can just figure out the x-intercept, right? Because we see where it hits the x-axis. So we can write this as a minus t minus 2. All right, well, what about this pattern? Well, again, we can just figure out the x-intercept. So this is t minus 2. And here, it would be a minus t minus 4. And then t minus 4. And then a minus t minus 6. And then a t minus 6. And dot, dot, dot. Okay, so we can see what the function is doing in each part. Well, now what we want to do is translate that into an expression that we can use with Laplace transform. So we want to somehow get it down to, if we can, one line. All right, so we start. And the way we start these expressions is we're going to start initial behavior, and then come to our first change in behavior, on, off, go to our second change, and so forth and so on. And with our goal to say, is there a pattern? Okay, so our initial behavior is pretty easy. It's t. So we have that our function looks like t plus change in behavior at 1, which means we're going to do an on-off switch, u of t minus 1. And now our behavior afterwards is t minus 2 with a negative in front, and subtract the behavior before. So in this case, t. Now we go to our second place where we change, which is at time 2. So u of t minus 2. And our behavior afterwards is t minus 2. And we're going to subtract the behavior that came before. So subtract minus t minus 2. And then we go to our next place, t minus 3. Okay. So u of t minus 3. And then what's going to happen? Well, our behavior afterwards is a minus t minus 4. And then we're going to subtract a t minus 2. Okay, to our next one, u of t minus 4, because we're going to switch our behavior at 4. Afterwards, we're at t minus 4. And before, we're at minus t minus 4. And well, we're running out of room, so we'll say dot, dot, dot. And dot, dot, dot is secret mathematical language for, and the pattern continues. Well, if there is a pattern, well, let's hope so. Because really, patterns are the only chance we have if we have anything that goes on forever. You know, if there's anything going on to infinity, you really need a pattern, or you're in trouble. Well, we don't want to be in trouble, so let's look for patterns. Okay, so let's clean this up. So t becomes t. Now here we have a minus a t minus 2 and a minus t. Now if you look at this, work it out, this becomes minus 2t plus 2. Well, we really want to make it look like a t minus 1. We say, oh, pull out a minus 2. So we can write this as minus 2 times t minus 1 u of t minus 1. Okay, how about this next one? Well, it becomes t, and there's a plus t, so that becomes a 2t and minus 4. Well, we want it to look like t minus 2, so I'll write this as a plus 2, t minus 2, u of t minus 2. Oh, all right, this is looking pretty promising. Well, let's see if it keeps going. Here we have a minus t and a minus t that makes a minus 2t, a plus 4 and a plus 2, which makes plus 6. We want it to look like t minus 3, so we pull out a minus 2. So minus 2, t minus 3, u of t minus 3. Oh, all right, that's really promising. Here we'll get a t, and there's a plus t, so there's a 2t, a minus 4, and a minus, a minus, a minus. Lots of minuses, but becomes minus 8. And so we'll have plus 2 u of, whoops, sorry, got ahead of myself, 2 t minus 4 u of t minus 4. And now we say, okay, is there a pattern? Well, oh yes, there's always the 2's. We alternate our sign, and then we have a t minus 1, t minus 1, t minus 2, t minus 2, t minus 3, t minus, so forth and so on. So actually, yeah, we can spot the pattern. And now we're ready to take the Laplace transform. So the Laplace transform of f of t is equal to, well, take the Laplace transform of each part. So t becomes 1 over s squared. Then we have minus 2. And when we see this u of t minus 1, we have our rule that says, just remember, Laplace transform of u of t minus a, f of t minus a, is equal to just f of s e to the minus as. All right, so there's that rule on the side. So here, this is really the function t that's been shifted. So we again have a 1 over s squared, and it'll be e to the minus s, plus 2, 1 over s squared, e to the minus s, minus 2, 1 over s squared, e to the minus 2s here, excuse me, and then e to the minus 3s, plus 2, 1 over s squared, e to the minus 4s. And in fact, we can keep this pattern going, right? We know where it's going to go from here. It's going to be minus 2, 1 over s squared, e to the minus 5s, plus 2, 1 over s squared, e to the minus 6s, and dot, dot, dot. Now, in some sense, you could say, we did it! Because we did. This is actually a correct answer. We were asked for a Laplace transform. We found a Laplace transform. Life is good. And we could walk away from this problem. But we're not going to. We're going to say, hey, could we write this in a nice, simple way? And we say, okay, well, what are some things we could do? Well, here, everything has a 2 except, of course, this first term. We kind of like the first term to be like a 2. So, okay, we can fix that. So let's think of this as minus 1 over s squared plus 2 over s squared, and so forth and so on. All right, and you're probably thinking, well, that doesn't really do much. Why are you doing that? Well, I want things to look the same as much as possible. And in particular, everything has a 2 over s squared now. So we have that minus 1 over s squared in front, plus 2 over s squared times, and let's see what we have. We're going to have 1 minus e to the minus s plus e to the minus 2s minus e to the minus 3s, and so forth and so on. Oh, okay. Cool. But you're probably thinking like, Steve, you still have it, dot, 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 dot. Yes, but notice something here. This is actually can be rewritten yet again. And I know, you're like, Steve, that's you're always here doing that, right? We're always rewriting things. Well, yeah, because that's how math works. You keep rewriting things until things get simple. And in particular, the moral here is this is the same as minus e to the minus 1, minus e to the minus s to the 1. Here, this is minus e to the minus s to the 2. This is minus e to the minus s to the 3. Minus e to the minus s to the 4. In other words, this is a geometric series. So how does that help us? Well, turns out there's a nice fact that says the sum 0 to infinity of r to the k is equal to 1 over 1 minus r. So we say, oh, in fact, even this 1 here, this is minus e to the minus s to the 0. So this is the geometric series where minus e to the minus s is r. So what do we have? Well, this is minus 1 over s squared plus 2 over s squared times 1 over 1 minus e to the minus s. And yeah, there we go. So we can rewrite it just a little bit here. Minus 1 over s squared plus 2 divided by s squared times 1 plus e to the minus s. And we're done. It's beautiful. It's beautiful. In fact, there's a general principle which says if you have anything which is repeating, which is what we have here, then it turns out you can do a very similar argument to say, actually, once I have what the behavior is for a part of it, the rest of it will be a geometric sum. Because if you look at the definition of the Laplace transform, the only thing that's changing it is that you're shifting over, which is adding an extra term of e to the minus ks, where k is your shift. And so you end up with things that have this type of expression inside of them. What a fun problem. All right, well, cool. I hope there's lots of more fun problems to come. I think there will be. Find the inverse Laplace of, upstairs, 3s minus 11, e to the 12 minus 3s, downstairs, s minus 4 quantity squared. And we're told to simplify as much as possible. Well, that probably is an indicator that it does simplify. And hopefully as much as possible. In particular, we are kind of expecting there to be a really nice answer. And you might say, well, it doesn't look very pretty now. But yeah, that's often what happens. Things that don't look pretty, when you run it through the process, become pretty. And vice versa. Things that look pretty, run it through the process, oh, terrible looking. Okay, so what to do? Well, we see we have some terms downstairs, so we're like, aha, partial fractions. But we remember the principle. The only time we can do partial fractions is polynomial upstairs, polynomial downstairs. We got to pull off this exponential term, move it to the side. So we have the following. This is the same as 3s minus 11 over s minus 4 squared times e to the 12 minus 3s. And we're going to do things individually to those two pieces. Now the exponential part, we'll take care of that really quickly. The thing is, we don't really like it in the form e to the 12 minus 3s. So we're going to rewrite this as e to the 12 times e to the minus 3s. And that 3 there tells us we're going to have a shift by 3 in our answer. Okay, so now for the polynomial over polynomial part, we say, great, this we can run partial fractions on. So that's what we're going to do. Partial fractions, here we come. So, well, downstairs was already factored for us. So we can say that 3s minus 11 over s minus 4 squared is something over s minus 4 plus something over s minus 4 squared, right? We gotta work our way up. Clear denominators, and in this case, that means we multiply by s minus 4 quantity squared, and we'll get 3s minus 11 is equal to a times s minus 4 plus b. Okay, well, we can do all sorts of things here. I like to plug in values, but since the only nice value is 4, okay, we can do that. We can plug in 4, why not? Might as well get low-hanging fruit. S equals 4. We get 12 minus 11, which is 1, is equal to 0 plus b. All right. Now, there's no nice values in that you get cancellation of terms, but you also say, hey, what makes s minus 4 nice? Now, 4 does, but we could also say 5 does, because that's pretty simple. We get 15 minus 11, which is 4, is equal to a times 1, a plus b. We know what b is, plus 1. So a plus 1 equals 4. That says a equals 3. All right, so good. We now have the following. We can rewrite what we're going to take the Laplace inverse of. And remember, most of the work in taking Laplace inverses is the rewriting. So we've done the hard part. We have e to the 12th, which is a constant. So we'll go ahead and put that near the front. And then we have our a, which is 3 over s minus 4. And our b, which is 1 over s minus 4 squared. And then we have that e to the minus 3s. Well, we really should have done, and we'll do it now, 3 times 1 over s minus 4 plus 1 over s minus 4 quantity squared. All right. Now, when we're preparing to take this inverse Laplace transform here, we say, okay, what are the contributions for the different parts? So we say, okay, this is a constant, so it's just going to be what the constant is, e to the 12. And similarly, the 3 goes to 3. Now, 1 over s minus 4 is on our sheet. So it's, if I see e to the ct, Laplace transform e to the ct is 1 over s minus c. So this is e to the 4t. Now this 1 over s minus 4 squared is a combination of two facts. Namely, Laplace transform of t is 1 over t squared. And then Laplace transform of e to the ct times some function, capital F of s, is f of s minus c. So when we see a shift, that means there was an exponential function, in this case e to the 4t, and then the unshifted is 1 over s squared, which becomes t. So the punchline is this is going to become our t e to the 4t. Now, this part right here tells us a shift by 3. Okay, so we know what's happening to our individual pieces. So when we put it all together, what do we have? Well, we have e to the 12 times 3e to the 4 parenthesis, because, you know, parenthesis is good, safe, good place to save points, right? And then plus t minus 3 e to the 4 t minus 3, because we have to shift by 3 everything that's attached to that. All right, and then remember we also have our on-off switch. Now, this is our inverse Laplace. We would be done if it wasn't for this sentence, simplify as much as possible. Okay, well, so we should simplify. Some things we can do, well, we can pull out common terms here. So we have our e to the 12 in front, and this exponential is also common, and notice we can distribute. So that's e to the 4t minus 12. We'll come back and work with those. And we have 3 plus t minus 3, and then we have u of t minus 3. Now, in the first part, when we have multiplication of the exponentials, that becomes addition. So this becomes e to the 4t. 3 plus t minus 3, well, the 3's cancel, so we end up with t. And then the u of t minus 3 becomes u of t minus 3. Yeah, there's not a lot we can do about that one, but I can't think of anything that you could do to simplify that expression. So our answer, t e to the 4t, u of t minus 3. A lot simpler than we may have thought when we first looked at it. Says, oh yeah, it does simplify rather nicely. Well, that's the way math works. Things that look complicated can become simple. Things that look simple can become complicated. There's probably a life lesson in that, but I don't know. We'll figure that out one day. Solve for x of t, where x double prime plus x prime is equal to 1 plus 2u t minus 2. And there's initial conditions, x of 0 equals 1, x prime of 0 equals 0. All right, well, all right, let's see. What can we do? What can we do? Well, the answer is we just run the process. We don't have to think about it. Even when this right-hand side is something where there's step functions or maybe even delta functions involved, it doesn't change our approach. We always do things the same way. All right, so for us, we're going to use Laplace transform because that's what we're practicing, but also because Laplace transforms are really good whenever you have piecewise functions, in other words, u's, or impulse functions, in other words, deltas involved. All right, so we can say that the Laplace transform of x double prime plus the Laplace transform of x prime is equal to Laplace transform of 1 plus 2 Laplace transform u of t minus 2. All right, so let's go through and work on these terms one by one. Namely, we'll start with the Laplace transform of x double prime. Now that is equal to s squared capital X minus s times x of 0, which is 1, and then minus x prime of 0, which is 0. Plus, now we go to Laplace of x prime, that'll be s capital X, and then we're going to subtract our x of 0, which is 1. And that's going to be equal to Laplace of 1 is 1 over s plus 2. Now here, Laplace of u of t minus 2, you can actually think of this as 1. So that's why there's a 1 over s. And then it's been shifted by 2. So that's e to the minus 2s. All right, good. So now what? Well, we solve for capital X. So we'll get s squared plus s times capital X is equal to, on this other side, we're going to have a s plus 1, right, because that becomes s plus 1, and then a plus 1 over s, and a plus 2 over s, e to the minus 2s. And, well, so this s squared plus s, of course, is the same as s times s plus 1. And when we divide, we get the following. X is equal to Well, s plus 1 over s times s plus 1 plus 1 over s squared s plus 1 plus, all right, this has 2 times 1 over s squared s plus 1 and e to the minus 2s. Now, we could have put things together, but in this case, it may have helped us to keep things separate. Because you'll notice in our first part, the s plus 1s cancel. We're like, yeah. And now, the other part, you say, oh, look, these are going to match. Well, what does that tell us? Well, it tells us we are only going to need to do partial fractions once. And whatever works here also works there. Well, that's going to make things a little bit simpler. And we like things which are a little bit simpler. All right, well, let's see. What do we have? 1 over s squared times s plus 1 is going to look like something over s, something over s squared, and something over s plus 1. Clear the denominators, which means multiply by s squared times s plus 1. And what do we get? Well, we're going to get a times, and now in this case, one of the s's cancels, so it's just a single s and an s plus 1. In the second case, both the s's cancel, so it's s plus 1. And in the last case, we get c s squared. And all that equals 1. Okay, well, let's pick wisely, as much as we can. So, some wise choices. We could choose s equals 0. And that knocks out the a and the c term. And we get that 1 is equal to 2b. Well, or is it not 2b? Well, we just want b. So that tells us, oh, b is a half. All right, let's choose s equals minus 1. Well, what happens there? Wait, why did I write 2b? No, I thought s equals 1. No, s equals 0. 1 equals b. b equals 1. Oh, my goodness. Oh, no matter how long you've been doing this, it's easy to make silly mistakes, which is why it's okay to pause and say, wait, that doesn't seem right. Okay, s equals minus 1, and we'll get 1 equals c. Okay, great, c equals 1. All right, any other nice choices? Well, how about 1? So s equals positive 1. We get 1 is equal to a times 1 times 2. 2a plus 2b. Well, b is 1, so plus 2. Plus c. And what do we see? Well, the 1s could cancel. 2a plus 2 needs to equal 0. It says a needs to be minus 1. All right. So, updating. What do we have? Well, we have the following. The first term is 1 over s. Now, the second term is what? Well, you replace it by what we have here. So it's a plus a minus 1 over s plus 1 over s squared plus 1 over s plus 1. Then there's a plus 2 times, and then it's the same thing. We have a, well, I can just copy it here, right? Minus 1 over s, a plus 1 over s squared, a plus 1 over s plus 1, e to the minus 2s. All right. Good. Good. Okay. So we're almost there. We're almost there. But you might notice, ooh, very nice cancellation. As if it was meant to be. Okay, let's think about our pieces here. When we're thinking about our inverse Laplace, we say, look, 1 over s squared becomes t. 1 over s plus 1, e to the minus t. 1 over s is 1 over s squared, t, 1 over s plus 1, is, again, e to the minus t. But remember, there's also a shift by 2 that's involved in that last part. So we're ready to almost write down our final answer. Well, other than maybe simplifying. So we have that little x, which is what we're after. Inverse Laplace of big X is t plus e to the minus t, good, plus 2 times, and then we have a minus 1 plus t minus 2, because we're replacing all the t's by minus 2's, plus e to the minus t minus 2, and then u of t minus 2. Now, we're pretty much, not much we can do, except, we can combine this minus 1 with that minus 2. So we could say, okay, so this is t plus e to the minus t, and plus 2 times t minus 3 plus e to the minus t minus 2, u of t minus 2. And done. Except that looks suspicious. There we go. I don't know why my t's looked like a 2 in that place. Well, bad handwriting. It actually comes back and haunts you sometimes. Have you ever had that experience when I can't even read my own handwriting? Well, I have, and that's tough when you're on a test. I strongly recommend, write legibly. It's very helpful. All right, well, that's good. Let's do some more. Solve the following differential equation using Laplace transform. And we have y double prime minus 2y prime is equal to u of t minus 1 times 4 cosine 2 t minus 1 minus 4 sine 2 of t minus 1. Okay, all right, with y of 0 equals 2, y prime of 0 equals 4. Okay, well, this will be fun. Well, what do? You do what you always do. We start the process, right? We're going to take the Laplace transform of both sides, and fingers crossed, things are going to be nice. Now, they were very, very kind to us in that they already had things shifted. Oh my goodness, if these weren't shifted, hopeless. But we have hope now. Okay, so we can say Laplace transform of y double prime minus 2 Laplace transform of y prime is equal to, well, the Laplace transform of this whole expression. All right, well, this will be fun. Okay, well, that doesn't feel like we did much, but all right. Let's start with the Laplace transform of y double prime. That's something. That's something we can say. This becomes our s squared capital Y minus s times y of 0, so times 2, minus our y prime is 0, which is 4. Okay, and then we're going to subtract 2, parenthesis, saving points, and we're going to have s capital Y subtract y of 0, so we're going to subtract 2. All right, on the other side, well, we see this u of t minus 1, so that's going to come in e to the minus s. Might as well put it in the front. Doesn't really matter whether it's in the front or the back. That's how multiplication works. Now, if we'd had the unshifted version, this would be cosine of 2t. And cosine of 2t, it's on our chart. So the 4 is the constant, and cosine is the one which has an s upstairs. And so this would be s over s squared plus, and then it would be this 2 squared. Then we're going to subtract 4, and now here it's sine of 2t. And for sine of 2t, it's, well, downstairs it's s squared plus 2 squared, and upstairs is a 2. All right, Good. Well, time for us to clean up. And hopefully stuff does clean up. Now, you might notice here, this minus 2 times a minus 2 makes a plus 4. And then we have this minus 4 here, so that those actually cancel. Something canceled! Oh, happy day. Happy, happy, happy days. All right. So, well, let's see. So what do we have here? We have s squared minus 2s capital Y. Move that 2s across. That's equal to 2s. And then plus, well, we'll say e to the minus s. And we'll go ahead and push these together. Then we have a 4s minus 8. Divide that by s squared plus 4. Okay, well, divide, and we'll have a nice idea of what y should look like. So, y should look like the following. We're going to have 2s over, and here we have an s squared minus 2s is s times s minus 2. And then we'll have e to the minus s. This 4s minus 8, well, I'm going to write this as 4s minus 2 for a second. We have s minus 2, and then s squared plus 4. And I know it's looking bad, but we haven't written down what cancels. S's cancel, s minus 2's cancel. So we don't need to do anything for this first term. It's good to go. We do need to do something for the second term because we have an s and an s squared plus 4 downstairs. All right, so the punchline here is we need to do partial fractions on this part. All right, so, but besides that, it's actually, all things considered, not too bad a shape. We've seen worse. We've dealt with worse. And now we'll deal with this one. All right, so we have the following. 4 divided by s times s squared plus 4. Well, it looks like something over s plus bs plus c over s squared plus 4. This is an irreducible quadratic, so we have that extra term upstairs. All right, clear the denominators. S times s squared plus 4, multiplying through, we get that 4 is equal to a times s squared plus 4 plus bs plus c times s. Okay. Well, we could plug in s equals 0 really quickly. Might as well. If we do that, I'll switch colors here just since we're into our solving coefficients phase. If we plug in s equals 0, we get that 4 equals 4a plus 0. So a equals 1. Now, there's not lots of great choices. At least there's not a lot of great choices if we don't want to get too complicated. So, trying to keep things simple, we will avoid plugging in complex roots. And, well, let's gather our coefficients. So a times s squared plus 4a, of course, we know a is 1, plus bs squared plus cs. Well, that's really what? A plus b s squared plus c times s plus 4a. And now we compare it to the other side. Well, 4a has to match with 4. It tells us a equals 1, which we knew. C, there is no s on the other side, so this has to be 0. Okay, that tells us c equals 0. And a plus b has to equal 0. Oh, since a equals 1, that says b equals minus 1. So we know our terms. All right. So, good. Let's update our capital Y. So we have that this is equal to 2 times 1 over s minus 2 plus e to the minus s times, we have our a over s, which is 1 over s, then our b times s plus c. Well, that's a minus, and here, don't forget, this is a place where a lot of people have made mistakes before. This b is multiplied by an s, so don't forget that. That's actually great news for us. So that's s over s squared plus 4. Well, why is that great news? Well, we're ready to write down our answer because we know what happens to our parts. S minus 2 becomes e to the 2t. E to the minus s means shift by 1. 1 over s becomes 1. And s over s squared plus 4, it's right there. That's cosine of 2t before we've done our shift. And so our answer is 2 e to the 2t plus, we shifted by 1, so we have an on-off switch at 1, u of t minus 1, times 1 subtract cosine of 2t minus 1. And that's it. We're done. That's the whole problem. The whole kip and caboodle, if you will. I don't know if people still say that, but we just did. We're done. Wow. Well, we're done with this problem. There's always more problems. All right. Let's look at a problem with a delta function, which means that we smack, right? That's what you should think of the delta function as we whack our system in some shape or form. So a mass of 1 on a spring with spring constant k equals 4 starts with x of 0 equals 3 and x prime of 0 equals 0, which means that what we've done is we've stretched it 3 and we're going to release it. So okay. So x prime of 0 equals 0 means that there's no motion when you start. So that's why I say stretch string and at time 0, release. At time 2 pi, the mass is hit with a hammer, providing an impulse force of 8. In particular, x double prime plus 4x is equal to 8 delta t minus 2 pi. And solve for x of t. All right, so they gave us the formula. This is wonderful. In fact, they gave us more than we need. We don't even need to know any of this. We just have to say, oh, there's a differential equation, solve for x of t. This part, not important. Isn't that crazy? Well, it would have been important if it had said, set up the differential equation. And so it's nice to see, like, hey, here's sort of behind the curtain. Now, I said none of this is important, but actually there are two pieces that are very important, and that is our initial conditions. So we're going to use those. So don't forget about those parts. All right, well, let's begin. We start by taking the Laplace transform of both sides. So we have Laplace transform of x double prime plus 4 Laplace transform of x is equal to 8 Laplace transform delta. That's not how you write delta. Delta t minus 2 pi. There we go. That's how you write a delta. Sometimes when you write these Greek letters, they all sort of flow together, right? Okay, so x double prime, that becomes our s squared capital X subtract s times x0, which is 3, subtract x prime is 0, which is 0, plus 4 Laplace of x is x, is equal to, now Laplace of the delta function, well, that's just 8 e to the minus 2 pi s. Okay, so we can rewrite this as s squared plus 4 capital X is equal to 3s plus 8 e to the minus 2 pi s. And finally, we get that capital X is equal to, well, 3 times s over s squared plus 4 plus, now here, looking ahead, we're going to have an s squared plus 4 downstairs. And upstairs we want a constant. So we say, well, what's the right constant? If we have s squared plus b squared, we want b upstairs. So in our case, 4 is 2 squared, so we want a 2 upstairs. So that leaves us with 4 and e to the minus 2 pi s. And now we're almost done. We're actually surprisingly close. And you're like, but we just started, Steve. I know. Sometimes problems go quickly, and that's okay. It's okay that they're not so bad. All right, so why? Well, s over s squared plus 4, it's on our table. This is cosine of 2t. And 2 over s squared plus 4, it turns out that's also on our table. What is that? Well, that's going to be sine of 2t. And then we don't forget, there's a shift by 2 pi. All right, so we know what our individual pieces are. And so we can say, aha, our answer for x, which is the inverse Laplace of capital X, is 3 cosine of 2t plus 4 sine of 2 t minus 2 pi. And then we have our on-off switch, u of t minus 2 pi. Now, we can clean this up a little bit because notice here we really have 2t minus 4 pi. And we say, if I have sine and I subtract 4 pi, that's like going around the circle twice in the opposite direction. But the moral is, it doesn't really change anything. So we could say, this really behaves like 3 cosine of 2t plus 4 sine of 2t u of t minus 2 pi. And there we go. Now, for all of you math lovers out there, who's not a math lover? Of course we love it. It's a beautiful subject. You might be asking the question, well, what does this say about our system? Well, what it says about our system is that initially it looks like the cosine function with a height of 3, and that goes on for one time period of 2 pi, but of course because there's a 2t on the inside, that says it's going to have 2 revolutions. Okay, so our spring is basically back to where it started. And then what happens is you hit it, and so what's going to happen now is that it's going to cause it to bump up. And in particular, if you look at your 3 and your 4, it turns out 3 squared plus 4 squared is 25. So it's now going to go up to a height of 5, down to a depth of 5. And so that from there, you will get up. And then it still has the same period. It's just going to have higher and lower oscillations. And so that's the picture of the behavior of the spring. So in particular, you can say this point, that's where our little impulse force came from. And it caused it to shoot and start oscillating into a bigger oscillation. And in fact, you could use this information, or in general, you could use a differential equation to say, I have something oscillating. When's the right time to hit it, and with what amount of force, to get my oscillations to either increase to a certain amount or to decrease to a certain amount? And so that's an application that we can do with differential equations. Sounds pretty good. Well, anyways, we should do another problem. A mass of 1 on a spring with constant k equals 4 starts with x of 0 equals 0 and x prime of 0 equals 0 and an external force acting of cosine 2t for 0 less than or equal to t less than 2 pi. And after time 2 pi, the force is turned off. Solve for x of t. All right, so what do we have here? Well, this is not a delta function. There's not a pulse. What it is that there's something that's on-off. Now you might say, well, what's the clue that we have an on-off? Well, this phrase, turned off, right? So whenever you see something that says turned off, well, that says, oh, wait, on-off. Okay, that's not so surprising. Now here they didn't give us a differential equation, but that's okay. We're pretty good at that. We see a couple of things. We see a mass of 1, and so you might remember there's our mx double prime plus our cx prime plus our kx equals our f of t. So, right, we have all these pieces. It's good in case we need them again, like on a final or something. The mass is 1. Spring constant is 4. No damping is mentioned, so this will be 0, since there's no damping given. Our external force, well, okay, so this one we have to be careful of. It's cosine of 2t, but it gets turned off at time 2 pi. So what does that mean? Well, that says we're going to have a u of t minus 2 pi, and then after time 2 pi, there's nothing. And then we subtract cosine 2t. All right, good. So that's our differential equation. And you say, okay, are we ready? And you might say, ready for what? Are we ready to take the Laplace transform? And why not? Well, we're almost there. There's just a small hitch. So let's take care of that small hitch. It's right here. That is our problem. So we have x double prime plus 4x is equal to cosine of 2t. And u of t, well, all right, we'll write it as u of t minus 2 pi. Subtract, on this side, there's a subtract. And now, the thing is, we need this to be t minus 2 pi. So we do what we ought to do. This is cosine 2 of t minus 2 pi plus 2 pi. Okay, so which is the same as cosine 2 t minus 2 pi plus 4 pi. And then we say, cosine repeats itself every 2 pi. And so this is just the same as cosine of 2 t minus 2 pi. All right, good. Now, what do we have? Well, from here, we get the following. We're ready to take our Laplace transform. So, the Laplace transform of x double prime plus 4 Laplace transform of x is equal to the Laplace transform of cosine 2t plus u of t minus 2 pi, and Laplace transform of that, times minus cosine 2t minus 2 pi. My handwriting is absolutely atrocious here. Okay, all right, well, we're among friends. We know what we mean, right? That's all that matters. As long as we know what we mean and that we get the right answer, then we're fine. Life is good. Well, what do we get? Well, we get a couple of nice things here. We get an s squared and capital X plus a 4 capital X is equal to, and here we're going to get cosine of 2t is s over s squared plus 4. And then we're going to get plus e to the minus 2 pi s. There's a minus 1. And then, same thing, right? S over s squared plus 4. Okay. Well, divide through, and we get that, well, I should say factor first, because this is s squared plus 4 capital X. Notice we used our initial conditions being 0. That's why things simplified. So we get that capital X is equal to s over s squared plus 4 quantity squared and minus s over s squared plus 4 quantity squared and e to the minus 2 pi s. All right, good. Now, at this point, you might be saying, hey, cool, partial fractions, except you've already partial fractioned it. There's no more partial fractions to do here. It's as partial fractioned as it can get. So you say, okay, if it's as partial fraction as we can get, does this look like anything on our table? Well, it turns out we do have something on our table that looks pretty close to this, right? Namely, if you remember, the Laplace transform of sine of t, well, that's equal to, sine of, let's get this right here. Laplace transform of sine of b times t is equal to b over s squared plus b squared, and the Laplace transform of t sine of bt is what? Well, you take the derivative, put a minus sign, you end up with 2bs over s squared plus b squared. Okay, so that's what we have. So, and I forgot to say squared. So, this is very close to that. And the only thing that's missing are some 2 times 2's, right? Because this is 2 squared, so we'll write this as 4 and put a 1/4, and we'll write this as 4 and put a 1/4. All right, so this is on our table. So we're not like, do I have to remember this? No. On the table. So we're ready because we say, aha, this part right here, this is going to be t and sine of 2t, and this will also be t sine 2t, and this is shift by 2 pi. So we're now ready to put it together and say, well, what's the answer? Because that's what we want to know. Inquiring minds want to know. Well, so we have little x is the inverse Laplace of big X is 1/4 t sine of 2t, and then minus 1/4, and times, we have to shift everything by 2 pi, t minus 2 pi sine of 2 times t minus 2 pi times u of t minus 2 pi. Okay. And is this our answer? Yes, it 100% is. That is indeed our answer. But this looks like we could clean it up. And so we will. We're going to clean this up. So the first thing is, we've been doing this a few times. If you've been watching this video, this is the same as 2t minus 4 pi on the inside of the sine, which really says, look, this is really sine of 2t. All right. So we're going to do this piecewise. So, okay, what happens before 2 pi? Well, before 2 pi, we haven't turned our on-off switch. So we have 1/4 t sine of 2t. Okay, what happens after time 2 pi? Well, so this is 0 less than equal to t less than 2 pi. At time 2 pi, we are going to see the following. Namely, we're going to see 1/4 t sine 2t, which is what we had. Subtract 1/4 t minus 2 pi sine of 2t. Well, so this is for t above 2 pi. Now, that's 1/4 t sine of 2t. Subtract 1/4 t sine of 2t, because you just distribute, and then plus pi over 2 sine of 2t. So that means we have two behaviors. 1/4 t sine of 2t from 0 up to 2 pi, and pi over 2 sine of 2t, and that's for t above 2 pi. And there we go. Now, in terms of the picture, what does that say? Well, what it says is that initially we're bounded up and below by 1/4 t, and then we're bounded by a pi over 2. So we have the following behavior, namely we go up and down, and let's see, I want to make sure I get the right number of counts here. 1 to there. So this is at our 2 pi, and then we just oscillate from then on. So initially our external force, we're starting at 0. The external force acts to get our spring moving, and after the external force stops, the spring says, okay, I got you, and I'll just take it from here, and it just keeps oscillating up and down the same amount from there on out. So there we go. Yep, that's the behavior. All right, good. And actually, that was our last problem. Well, Laplace transforms, it was great to know you, and hopefully we'll meet again sometime, like the exam. All right, thanks for joining me, and hope you have a great day. Bye.